So I start recording and share screen. All right, is it looking okay? Good. Okay, so welcome back from spring break. I hope you had a relaxed time, at least for a week. Yeah, so we get back to the quantum field theory now. So just a reminder, what we did towards the end of the lecture before the spring break is to develop time-independent perturbation theory. And so we decided to take the interaction picture where the operators evolve according to the unperturbed Hamiltonian. And all the issue of the interaction is contained in this time evolution operator for states. And we came up with this symbolic notation as a solution for this time evolution operator as a function of the perturbation of the system V, which allows us to do the perturbative expansion in power series in this interaction Hamiltonian. And time order product had been defined in this fashion, and you have seen this already. And by using this time evolution operator, we can work out various transition probabilities in the in quantum systems. And we came up with, for example, second order result using this perturbation theory. So the first piece here is the first order perturbation theory, where initial state I goes to final state F directly using the perturbative Hamiltonian V. Second one goes through this virtual intermediate state. And virtual because this actually doesn't satisfy the energy conservation. And we came up with this little cartoon to depict these terms at various orders in perturbation theory. So the first order term can be depicted this way. Initial state hits this interaction Hamiltonian V, goes straight to the final state. On the other hand, the second order piece can be depicted this way. The initial state hits this interaction Hamiltonian V and goes through this yellow line called the propagator. And propagator has this form of what is called energy denominator. And EI and EM are typically not the same. Therefore, it doesn't satisfy energy conservation. And that's why this state is virtual. So this state is allowed to exist only with an uncertain principle, so only by a finite amount of time. And you have to give the energy back to the system by hitting another interaction Hamiltonian V, so that you finally go to this final state F, which does have the same energy as initial state I, which is enforced by this delta function of the energy conservation. So this is the idea of how you develop perturbation theory. And we started to actually use this. And the one thing we looked at is the 2 photon emission from the 2s state of a hydrogen atom down to 1s state. We did some estimates. We looked at the more precise calculations in comparison to data, and they all beautifully agreed. So that's the reminder of what we have done before the break. So what we like to do is to apply this second order perturbation theory into more processes, especially the scattering processes. So what we talked about so far is that you have a state in a discrete spectrum that decays into another state, which is also a discrete spectrum. And so that's the emission of the photons from atomic excitations. That's what we talked about already. But in physics, you often also talk about scattering process. So states are in the continuous energy states, labeled by just the kinetic energies. They are free particles, and they come together. And like in a pool, they actually sort of come together and then sort of bump against each other. And that's a scattering process. So we like to talk about such a process too, because that's something you can often do experiments on and measure quantities and get more information about the physics associated with the process. So we'd like to actually move on to talk about that kind of scattering process. And so this is just a name I introduced called propagator. And what we are mostly interested in right now is the interaction of the point particle and the photon described by this interaction Hamiltonian. So we're going to use this delta H as V in a perturbation theory and develop calculations for various processes. Okay, so this is just a reminder of what we are doing before the break. And so are there any questions about this? Everything okay? And right now you are looking at the process called the Thomson scattering, which is a scattering process of a photon and the free electron, not inside the atom, but the free electron. So in that case, taking the approximation that the electron is very, very slow. So you ignore the momentum of the electron. So the first two terms in this interaction Hamiltonian can be neglected. And the last term in a Hamiltonian has a squared in it. And so what you are being asked to do is put in this a squared into the first term in this perturbative expansion, namely first order perturbation theory. And initial state I has one electron and one photon. And this A would annihilate photon in initial state. Another power of A creates a photon that goes into the final state, but in a different direction, so that this describes a scattering process of an electron and a photon. So that's what I'm asking you to do right now. It's a pretty simple calculation because you can ignore all the momentum associated with the process as an approximation. And so in that limit, then only thing you need to look at is the first term, the first order perturbation theory. And just by looking into the matrix element with the annihilation and creation operator, you can work out the cross section called the Thomson scattering. And so that's the thing you are being asked to do in the current homework problem. But anyway, so for that purpose, you don't need to go to the second order in perturbation. Okay, questions? Everything okay? All right. So what we talked about in the case of the 2s decay was already an application of the second order perturbation theory, because 2s state decays into 1s state, not with one photon emission, but emission of two photons. And to emit two photons, you have to consider the second term, second order perturbation theory, because what you have to compute is the 2s state can go to 2p state with this first matrix element and has this energy denominator. And then 2p state goes to 1s state with the second matrix element. So 2p state in this case is the virtual state. And to be precise, this is a state with 2p with one photon. And you do similar things for 3p, 4p, and so on. And you have to add up all the possible intermediate states in this process. And that's how we computed this two photon process. And for the hydrogen, as far as I know, that this process had not been measured because it's too slow. With too slow meaning it's too rare to be observed. But if you go to higher charges, then the process gets enhanced by the atomic number, I think the fourth power. So then it becomes faster and becomes observable. And then you see the beautiful agreement between theoretical calculation, as I outlined, and the experimental data. So they agree very well with each other within the error bars of the experiments. So that's how you can use the second order perturbation theory to compute the process, which didn't happen at the first order perturbation theory, but does happen at the second order perturbation theory. You can go ahead and compute it, and then you can compare that to the experimental data. So that was basically what we finished up discussions before the spring break. Okay, let me pause here again. Are there any questions about that? Okay, there doesn't seem to be any. All right, then we move into a new subject, which is the scattering of a photon of an atom. And the scattering process, as I already mentioned, is that something is hitting something else, right? That's obviously the idea of scattering. So in our case, what we are talking about is that you have an atom that has electrons in it, in, let's say, ground state of hydrogen, for example, and you send in a photon, and the photon would interact with the electrons inside the atom and get scattered in off direction. So that's the scattering process of our interest. And what we talk about in that case is the probability of this scattering called cross-section. And just in case you haven't heard of this idea, cross-section is a rate. Remember, rate is the probability per unit time. The rate per flux of photons you send in for this scattering process. So it's not just rate, which we computed the Fermi's golden rule. You have to normalize it further by the amount of photons you send in to the scattering process. And so that's why cross-section has really the unit of the cross-section. So just to make sure that is the case, rate is the probability per unit time. So the rate has a unit of inverse time, obviously. And we need to also understand what flux is. Flux is the number of particles you send in per unit time per unit area. So if you're sending a bunch of photons randomly, so thinking about, for example, throwing darts on the target, then the target has a finite area, and you send in some certain number of darts per unit time. So that gives you this flux factor. So per unit area per unit time is the amount of photons you send in to get scattered by the atom. So the idea of the word cross-section is that this is the rate per flux. So the unit would be, the rate is inverse time, and you divide it by the unit of flux, that's inverse area, inverse time. Inverse time cancels between rate and flux. Inverse area is in the denominator, so that gets brought to the numerator as the area, and hence here's the unit of the cross-section. So very roughly speaking, cross-section is the size of the target you are trying to hit. So as I said, if you're trying to throw darts at a target, the entire target measures this area for the flux. But the cross-section we are talking about is the probability to hitting this bullseye at the very center. And so the area of that center is the cross-section, which tells you how often you are likely to hit the way you would like to hit. So the cross-section really does have the meaning of the area, because that tells you how often you can hit the area you would like to hit with your darts. And so that's the idea of the word cross-section. So whenever you talk about a scattering process, we talk about cross-section of the scattering, or scattering cross-section as a single scientific term. So as I said, this has the meaning of the size of the target. So the only thing you need to know beyond what you have done with Fermi's golden rule, you already know how to compute the rate, right? So the only thing you need to know is what the flux is. And in the box normalization we are using, you have one photon in the box of L cubed. And if you are sending in a photon, it comes with the speed of light. If you're sending some other particles, it would come in a speed which is less than speed of light. But anyway, we are talking about certain velocity to send the particles in. And if you boost the system to a different reference frame, then you're talking about the relative velocity rather. So in general, flux factor is the V relative between the target and the projectile over the volume, which has the correct dimension of 1 per area per time. So this is the flux factor. So beyond what you know how to compute the rate with the Fermi's golden rule, you divide the rate you compute by this factor of V relative over the volume. And of course, the volume is an artificial thing we are using for our normalization of the states. And so the volume factor is supposed to cancel at the end of the day. And you'll see that explicitly when you actually get to an example of this. So that's the idea. So in the end, the cross-section, which is often denoted by symbol sigma, is basically the same thing as the Fermi's golden rule, 1 over h bar, and this matrix element and the delta function in energy conservation, and summed over all possible final states in this sum, and divide that rate by this flux factor. And here I already assume that the one sending in the projectile is actually a photon, so that it comes with the speed of light c. So that's the idea of the scattering cross-section. So this is basically a definition. And now that you have everything at your disposal, you know how to compute these matrix elements, including photon initial state and final state, because now you know that the vector potential is made of creation and annihilation operator of the photons, and you stick them in here, compute the matrix elements, sum over all final states with the delta function, and divided by the flux factor, and then comes out the cross-section of any process you're interested in. So that's the idea. Okay, so let me pause here and see if got some questions about this. Do you study cross-section in any other classes? You do? Which class is it, Gerardo?
I remember talking about it in physics 105 and 137B.
Ah, okay. And Dorothea is also nodding, so. Okay, good, good. All right, then you have seen this already. Good. And of course, I guess the most famous example is the Rutherford scattering. And in that case, you first compute the cross section with the classical mechanics by computing the trajectory of the heat of the alpha particle in the Coulomb potential. And you can do the same thing also in perturbation theory and in quantum mechanics. And for some magical reason, they come out to be exactly the same result. Okay, so that's the scattering process. And again, because of Dirac's notation, the initial state tend to be on the right, final state is written as a bra on the left. I just reversed the order of this picture. So the photon is coming from now the right, hitting the atom here, and then goes to the final state where photon is emitted in some off direction. So I just reversed the order of this initial and final, and then it matches up with what I'm writing in this formula here, that I is on the right and F is on the left. And we know what the interaction Hamiltonian is for the interaction between the point particle electron and the photon. So there are three possible processes you need to compute for this. The first one is use the last term of the interaction Hamiltonian, which has a squared in it, and use this term at the first order in perturbation theory in this first term in this big parentheses. So in this case, V is basically a squared, which contains two annihilation operators or two creation operators, or the cross term of one annihilation and one creation operator for photons. So using this a squared, initial state has one electron and one photon. Then A can annihilate one photon in the initial state and create another photon for the final state. And the final state photon may be in a different direction from the original direction of the photon, and hence the scattering process. So I can use the same kind of picture I used before, but now using this wavy line to indicate photon in the initial and final state. And this blob in the middle is supposed to mean this E squared A squared over 2m term in an interaction Hamiltonian. So that's the way you can describe this process. And this is the first order in perturbation theory because I have one blob in here. But if you go to second order in perturbation theory, you need to put in two blobs for the first matrix element and second matrix element together with this the energy denominator or propagator in between. And we indeed do need to have this. For example, this is one of the processes we need to compute. So in Coulomb gauge, I don't need to worry about the ordering of P and A. So you can just combine them together as E over PA. And I made a mistake here. It's supposed to have two in the denominator canceled out. It has only one power of E instead of E squared. So I'm going to correct that later on. So I apologize. But anyway, so I hope you see that this is just the first two terms of this interaction Hamiltonian. And then this interaction Hamiltonian has only single power of vector potential. So either only one power of annihilation operator or one power of creation operator. So what it can do is absorb a photon or emit a photon, but can't scatter a photon like this one, as we see for the first term in this diagram. So what it could do is that you have initial state of an electron and photon. Then electron comes in, and by using this operator, it can emit another photon, which is the different photon from what you have in inner state. So at this intermediate state, you have one electron and two photons. So energy denominator for the energy intermediate state should contain the energy of electron and this photon, which you just created, and the other photon, which was there from the beginning. So that's the intermediate state here, which you stick in to this sum. And then second use of the same operator can then annihilate the photon you had in initial state. So the initial state photon is now gone. And you end up with only electron from this part of the process. But the photon you created already at the first time of using interaction Hamiltonian is still there. So that's how you end up with a scattering process. So end result is the same as the first term, namely that you have the initial state electron and a photon, and then you have the final state with electron and photon. So that's yet another contribution to the scattering process. And finally, I'm sure you noticed this already, I can reverse the order between the use of two interaction Hamiltonians. So instead of creating the photon first, I can instead annihilate the photon first. So in this case, this operator, PA, annihilates the photon, which is already there in the initial state. So now this photon is gone. Intermediate state has no photons now, only one electron. And using the same interaction Hamiltonian, this time you use the creation part of the vector potential so that you create a photon in addition to the electron. So that's yet another contribution to the scattering process. So here, I'm using the same interaction Hamiltonian, but in different orders, whether the first use of the operator creates a photon and consider intermediate state both electron and two photons, or use the first interaction to annihilate the photon rather, and consider the intermediate state with no photons, but just the electron. So at the end of the day, you need to sum over these three contributions to the scattering process at the second order in perturbation theory. And I see some of you will chat into this. I haven't. Atomic physics, now I remember always. Okay. All right, Mashit. So if you haven't seen the cross-section, then that's totally okay. I hope I explained what this cross-section is supposed to mean. But if you have any further questions about this, you're welcome to ask, Rashid. Is it okay? Rashid? Are you there?
They said yes in the chat.
Okay, good, okay. Thank you. Thank you, Natalie. Okay, so I hope that's clear. So let me just go back before getting into actual calculation. So any questions about this slide? And I hope you can see that using this kind of diagram would let us understand things much more intuitively. And so this eventually become what is called the Feynman diagrams when we go to relativistic quantum field theory in a few weeks. So this is sort of the beginning of talking about these diagrams for the scattering process. And as I said already, so here's a typo again. So this block is supposed to indicate minus E over M, not E squared, no factor of 2 downstairs, P dot A. And I'm going to correct them later on after the class. Okay. No questions? Everything clear?
I have a question.
Okay, go ahead. Go ahead, Rayleigh.
So these the second two terms those are the only two terms that we would have to include in the sum for the second order perturbation.
That's right. For this process,
And,
yes.
Yeah, for a single photon in the initial and final state.
That's right.
Okay.
And depending on the process, you may need to go to yet high order process. For example, if you're talking about sending a photon in, it's an atom. And suppose you end up producing 2 photons at the end of the day. There can be such a process, but that would require going up to the third order in perturbation theory. And then you have various contributions at different orders, and you have to, again, sum them all up. Okay. And so the fact that you have to sum over all these virtual intermediate states is really part of the phenomenon that the quantum mechanics, everything interferes at the amplitude level. And so that's a really quantum nature of this kind of process. Any other questions here?
Just have a quick follow-up question.
Okay, go ahead, Rayleigh.
Does that mean that for that second order perturbation theory can only account for the single photon in the initial and final state then?
Second order
So if we have a different number of photons in the final state, we would have to go to third order in perturbation theory?
That's right. So if you have 1 photon in the initial state and 2 photons in the final state, you have to go to up to third order in perturbation theory. Yes.
Okay. Thank you.
And what we did before, though, is that you had only 1 electron in the 2s state of hydrogen. You had 2 photons in the final state, rather. And once again, the going up to second order perturbation theory was sufficient for that purpose, right? So you really need to think about what order is needed, but you can sort of do so just by knowing that blob can either annihilate a photon and create a photon with electrons coming in and out. So that's one way. Or you can have electron coming in, emit 2 photons into a final state electron. Or you can annihilate 2 photons for the electron into final state electron. So this blob can be used in 3 different ways. And this blob of P dot A can be used either the electron comes in and emit a photon, or electron comes in, absorb a photon. So you can use it in 2 different ways. And the minute you know that, then you can sort of glue these together to come up with these diagrams. Then this is intuitive enough that you wouldn't make mistakes in missing what terms you want to add in this big absolute square of the interfering amplitudes. So I hope that is pretty intuitive and clear when you actually think about what order and perturbation do you have to get up to compute some particular process you have in mind. Okay, good. Any other questions? All right. And we don't actually do the full calculation of this, but we go ahead and just estimate it. So this factor of h bar over 2 epsilon naught L cubed omega 2 or omega 1 on the frequency of the photon is the prefactor that appears in the mode expansion of the vector potential, if you remember. So this is there when you rewrite A inside this V using creation annihilation operators. So this is actually what comes out from the normalization of the creation annihilation operator inside the vector potential. And sum over all the final states of the photon, as we talked about this before, is given by this phase space integral normalized by 2 pi h bar for each dimension. We're talking about 3-dimensional space, so 2 pi h bar to cube power. And the phase space integral is the spatial integral, which is the volume of space. And the momentum integral, here I'm using the circle coordinates for that purpose. And the dq is actually canceled because energy conservation restricts the momentum of the photon in the final state to be the same as the momentum photon in the initial state. So photon comes in with the energy, which is speed of light times the momentum of the photon, because photon has no mass and always goes the speed of light. C times Q is the energy. So EI is C times QI for the initial state. EF is C times QF for the final state. And the phase space integral, of course, has dq over the final state, but dq integral can be done using this delta function because EF is nothing but C times QF. So that's why dq is now gone in this sum over the final states with the delta function. Then you see that Q is there, which is again the energy over the speed of light, which is h bar times the angular frequency over speed of light using de Broglie's relationship. So we know that Q squared goes like omega squared using h bar and c. So what I'm trying to do here is to count up the powers in omega that appears in this process. And it turns out the cross-section turns out to be proportional to the photon frequency to the 4th power, which is the behavior called the Rayleigh scattering, which I think you have heard about somewhere else, but let me go through that in a little bit more concretely. So what we are trying to do is to count up the powers in omega. And we are not going to do full detailed calculation of this, but we will see that the end result turns out to be omega to the 4th. And that is actually sufficient for the purpose of the later discussion, why the sky is blue, why the sunset is orange. So we are looking at the regime where the energy of the photon is much, much smaller compared to the excitation energy of the atom. And if you're talking about the hydrogen atom, you're talking about the ground state in oneness. And excited state, the lowest excited state will be 2p. So if the energy of the photon is much, much smaller than the energy difference between oneness and 2p states, that's the limit of this Rayleigh scattering. And in that limit, the cross-section turns out to behave like omega to the fourth power. So that's what I'm looking for. So it turns out that in this matrix element, there is actually non-trivial cancellations, so that the matrix element turns out to be proportional to omega squared, which is somewhat non-trivial. And if you look at the lecture notes, Photon, the PDF, you see actually how you can work out this cancellation so that matrix element is clearly proportional to omega squared. And it's fairly technical, so I don't go through this on slides, and please look at the lecture notes, but that's basically the end result of working out these matrix elements. And it turns out that everything is of this form at the end of the day. And here you see, again, see the dipole operator, X coming in into this matrix elements. So the initial state atom using this X operator goes to some excited state like 2p, and it comes back to the oneness state using the second X operator. So both of them are dipole transitions. And you do this in the opposite order as you have seen in this diagram, whether you annihilate the photon first and create a photon later. And the annihilation operator comes with the polarization vector, creation operator comes with the polarization vector complex conjugated. So you can tell that that is that order. So intermediate state has one less photon, namely only the electron. That's why I have this plus h bar omega here, because the intermediate state has negative h bar omega, and you subtract that, and hence this plus sign. Second term corresponds to the creating the photon first and annihilating the photon later. So that is the other diagram I talked about on the previous slide. So in this case, the intermediate state has one extra photon, and hence intermediate state energy is atomic state energy EI plus h bar omega. And you subtract that, and that's why h bar omega has a minus sign in the denominator. So that's how you can understand these two terms coming out from this, the sum over three diagrams I mentioned earlier. And the cancellation I just mentioned is that the first term ends up having the same form as the second two terms. And there's a cancellation between them. So I already rewrote the first term in this big parentheses into a form that looks similar to the other terms, and already achieved the cancellation, which is going to happen among them, and extracted this omega squared in the matrix element up front to the omega to the fourth. And the other factors omega I mentioned earlier, coming from this normalization of the creation relation operator in vector potential, leads to omega inverse squared once you square the amplitude. Sum over all possible final states is given by q squared factor of the spherical coordinate, which is obviously proportional to omega squared. So these omega dependencies cancel between this normalization factor and the phase space integral. So the only omega dependence that remains in the end is coming from omega squared behavior of the matrix element, which is squared, and hence omega to the fourth. And that's how you can understand this omega to the fourth dependence of the cross-section. So at the end of the day, if you fully go through this calculation, then the cross-section goes like this. So omega, which is the angular frequency of the photon, is c over the wavelength of the photon, right? So there's a factor 2 pi, but apart from that, so omega is basically 1 over lambda. So you can rewrite omega to the fourth as 1 over the wavelength to the fourth power. It's the same thing. And cross-section, as I mentioned, has a dimension of the area. Of course, it's a cross-section. So if you have the length scale to the fourth power downstairs, you need to put in the length scale to the sixth power upstairs. So just by knowing that, I can do a dimensional analysis, and the kind of distance scale that comes in for the atomic physics will be basically the Bohr radius. So you can guess the cross-section should go like Bohr radius to the sixth power over the wavelength of the photon to the fourth power. So only by knowing the power in omega, you can get a pretty good estimate of the cross-section now. So that's a dimensional analysis. And by knowing this, the dimensional estimate, then by knowing how many atoms there are in a typical gas, like the air, at the standard temperature and pressure, then you have a 1 mole of atoms in 22.4 liters of the gas. And then you can estimate what the mean free path of the photon in the atmosphere, a mean free path, which you are also being asked to compute in the case of the Thomson scattering of a photon inside the sun. Definition of the mean free path is the inverse of the density of the target times the cross-section. And just to get an idea what this means is that, well, so each target has this area given by this cross-section sigma. And in a unit volume, you have n of them. So the probability to hit any of these targets would be the number of targets times the area of each target, and that's this n over 6 sigma in a unit volume. So that tells you how far you would travel to hit any one of these targets. And so that would tell you the mean free path of the photon in this case. So basically that each atom would look like a target of size 8 to the 6 over lambda to the 4th from the point of view of photon. And you have all these atoms distributed inside the air. And you have the number density of atoms given by this number density n. So 1 over n sigma tells you, from the photon point of view, how far it can travel without hitting a single atom on its way. And that's the idea of the mean free path. So by knowing the density, you can estimate this mean free path by substituting in this estimate for the cross-section given by ball radius the 6th power by the wavelength the 4th power. I estimate that for the typical wavelength of visible light, like 4,000 angstrom, that's sort of a yellow light, and we know it's 4th power. And then you can just plug in the numbers and find that typical mean free path of the photon is like 1,000,000 kilometers. And that's actually good. If this were, let's say, 1 kilometer, then you would never see the sun because all the light coming from the sun gets scattered away before that reaches your eyes, then you would never see the sun. The fact that this mean free path is longer than the thickness of the atmosphere, which is something like 20 kilometers, is the reason why you can see the sun. The most of the light coming from the sun would directly enter your eye and hit the retina, excites the electron, and the electrical signal goes through a nerve and reaches the brain, and you think you have seen the sun. So that's good. So this already tells you that you can see the sun. But it also tells you that given that this mean free path goes like one of the wavelengths, the 4th power, mean free path for the red light and mean free path for the blue light are quite different from each other. So putting in like 7,000 angstrom for red, 4,000 angstrom for blue, actually blue is maybe a little bit shorter than this. But anyway, so you take the ratio of the wavelength, raise it to the 4th power, and you get an order of magnitude difference in the mean free path. So the blue light gets scattered 10 times more than red light in the atmosphere. So that's the behavior you understand just by looking at this 4th power of the frequency in computing this Rayleigh scattering cross-section. And when you look at this formula, one thing you notice is that when wavelength goes to infinity, the cross-section goes to 0. Why is that? Well, when the wavelength of photon is very, very long, as you all know, a wave cannot resolve structure which is smaller than the wavelength. So when the wavelength of photon is much, much bigger compared to the size of an atom, then the photon cannot tell that atom is made of the nucleus with surrounding electrons. It only sees the whole thing. But as we already talked about, photon interacts with matter only because of its electric charge. Interaction Hamiltonian we looked like E P dot A proportional to E, that's the charge of the electron, or E squared A squared. Again, E is the charge of the electron. So the interaction with the photon always goes with the charge of the object it hits. And the whole atom is neutral. So long wavelength photon cannot tell that there's anything charged inside of the atom. It thinks it's totally neutral object. And photon doesn't interact with the neutral object because charge is 0. So it doesn't notice it. So what long wavelength photon doesn't see neutral atoms, and therefore it doesn't scatter. But as the wavelength becomes shorter, going from red to blue, then photon becomes more aware of the structure at short distances and starts to tell just a little bit that atom has a charge inside, and then it can hit the charge inside, namely the electron, and get scattered just a little bit. It's only a little bit because it doesn't quite resolve what's inside the atom, because wavelength is much, much longer than the size of an atom we are talking about here. But at least starts to resolve this a little bit and can scatter. So this is barely scattering of an electron inside the atom, because photon more or less sees the whole atom as a neutral object it doesn't interact with. So that's why cross-section is suppressed by the Bohr radius, which is smaller compared to the wavelength of the photon we are talking about. And that's why cross-section is suppressed by the long wavelength by the fourth power. So that's how you can sort of intuitively understand why the large lambda limit will give you a small cross-section. And as the wavelength becomes shorter and shorter from red to blue and UV, then the photons start to see that there is an electron orbiting around the proton and can scatter more and more against it. And when it comes to the energy of the photon, which corresponds to the excitation energy, then it can be totally absorbed by the atom to excite the atom from the ground state to the excited state. So that's how the cross-section becomes a lot bigger when you go to shorter wavelength and higher energy photons. So that's how you can sort of see intuitively why you get this kind of steep power in the wavelength of photon for this Rayleigh scattering process. But anyway, from the calculation point of view, the only thing you needed to work out is this non-trivial cancellation between different terms of matrix elements that will make the matrix element go like omega squared. But now you see the reason why there should be this cancellation, because the cross-section is supposed to be suppressed for the low frequency or longer wavelength, because the photon would not see anything charged, and therefore you have some power suppression effects you are supposed to get from this calculation. And once you have that intuition, you would look for possible cancellation between these matrix elements. Then you do find the cancellation as long as you do the algebra correctly. And indeed, final result is suppressed by the fourth power of the wavelength. And that's the idea of the Rayleigh scattering. Okay, so I said a lot on this slide. So I stop here, and I'm sure you got some questions about this.
Can you explain how we got the factor of omega to the fourth power?
Yeah, so let me go through this once again. So this H bar of 2 epsilon naught L cube omega is a normalization that appears when you do the mode expansion of the vector potential using creation annihilation operators. So each creation and the annihilation operator has the normalization of the square root of this factor in it. And if you look at, for example, first term here, it has 2 powers of creation and 2 powers of vector potential, right? This is the term E squared A squared over 2m from an interaction Hamiltonian. So I have A twice in here, and first A has square root of this one for the first photon. Second vector potential has the square root of this one with the energy of the second photon. Of course, they are the same energy because energy conservation. And you have square root of this times square root of that. Inside this, you square the whole thing, so the square root goes away, and that's how you end up with these factors, which goes like 1 over omega squared. On the other hand, I'm supposed to sum over all possible final states, And sum over the final states is done by this phase space integral in the unit of 2 pi h bar cube. And phase space integral, of course, has q squared dq. But dq is an integral over the momentum of the photon, which is related to the energy of the photon, which is fixed by the delta function. So I can perform q integral right away using delta function. So that goes away. So out of the original phase space integral of dq cube, q squared times dq, and dq goes away, so that leaves only q squared left. And q, momentum of the photon, is the h bar times the frequency over speed of light. And therefore, this is proportional to omega squared. And this omega squared cancels omega inverse squared from this normalization factor. So I don't have any omegas here. And where omega dependence comes out is after doing this cancellation in the matrix element, you find this the matrix element overall has dependence of omega squared. And you square that. And that's how you get omega to the fourth for the cross section. So that's the steps I went through rather quickly. And I hope that makes sense. Is that okay, Natalie?
Yeah, that makes sense. Thank you.
Okay, great. Any other questions? So I basically explained two things at once, sort of calculational details, how you go about and do this calculation and get this result. And also sort of intuitive reason why the cross-section should be suppressed for long wavelength photon, because long wavelength photon doesn't resolve the structure of atoms. It only sees the overall neutral object, and the neutral object doesn't scatter a photon and hence suppressed at long wavelength. So I said both of these things on the same slide, but I hope you got both messages here. No questions? Okay, so once you know that this scattering cross-section of photon of an atom goes with inverse the wavelength of the fourth power, and blue light is 10 times more likely to get scattered by the air compared to red light. And that's the usual explanation of why is the sky blue and the sunset orange. So if you look at the sunlight, and you shouldn't do that because that would burn your retina, but suppose you do, then the sunlight comes through the atmosphere. And because the mean free path is something like 1 million kilometers, most of the light doesn't get scattered and goes straight into your retina. And that's how you see the sun. But if the sunlight goes through and gets scattered just by a tiny bit, which happens more for the blue light than red light, then the atom that scatters the photon coming from the sun would scatter the photons in all possible directions. And then this scattered light might also get into your eyes and hit the retina. So with this blue light coming from this direction is, from your point of view, not the direction towards the sun, but away from the sun. You're looking at the air, but because the air scatters the blue light that goes into your eye, you see blue light coming from the air. And that's why the sky looks blue. The red light is 10 times less likely to get scattered. So you see 10 more blue photons compared to the red photon coming from the air. So it looks blue because of that. So that's the reason why is the sky blue. On the other hand, if you look at the sun at the time of the sunset, then sun is not straight up from where you are, but sort of close to the horizon. So the sunlight goes through the atmosphere for a long distance. So it's much more likely the photon gets scattered while the photon travels through the atmosphere. So the blue light gets scattered away by quite an amount as the light travels through the atmosphere for many, many kilometers, like 10,000 kilometers or so. So many, many photons, blue photons, get scattered away. So they don't get through into your eyes very much. But the red photons don't get scattered even over this much distance. And so they still get into your eyes straight from the direction of the sun. So that's why when you look at the sunset, sunlight has lost much of the blue photons, but the sunlight still has most of the red photons. And that's why the light coming from the sun looks red. And that's why the sunset looks red. So that is something you have probably seen in some other classes, but now you know the precise origin of this phenomenon. You have quantum field theory. Vector potential is the creation-annihilation operator of the photon. And by using the standard Hamiltonian in quantum mechanics, you can go ahead and compute this Rayleigh scattering process as second-order perturbation theory. Then you learn that the Rayleigh scattering cross-section goes like 1 over wavelength to the 4th power, and therefore blue light gets scattered by the atom 10 times more than red light. And the minute you know that, you can understand why the sky is blue, because the blue light is 10 times more likely to get scattered by the atom in the air and can come from off direction, not from the direction of the sun, but can come from the off direction from the air into your eyes. And that's why sky looks blue. On the other hand, if you're looking at the sunset, the much of the blue photons get scattered away. They don't reach your eyes, but the red light still do. And that's why the sunset looks orange. So that's the understanding of why the sky is blue and the sunset orange based on the QFT calculations, which you have just seen on the previous slide. So that I hope would give you some satisfaction that now you understand everything from the first principle. Okay, any questions about this?
Now, what about why the oceans are blue?
Oh, the ocean, let me see, do I understand this? I'm not totally sure now. I believe it's the same thing. So the molecules of water scatters blue light more than red light. So when the light gets reflected by the ocean, then the blue light is more reflected than red light and gets into your eyes. I believe that's it.
Yeah, what we're taught when we're little, at least what I think is commonly taught, is that it's because of the sky. So I don't know, maybe it's like what comes first, the chicken or the egg, but I think we're taught that like because the sky is blue, for some reason that also means that like the ocean is blue, at least the way that we perceive it.
Okay, that may be true too. I'm not
but
sure.
That's out.
But if you look at the water in glass in your room without sunlight, don't you still think that it's a little bit bluish?
No.
No? Okay.
No, I think
then I'm
you
not
get
sure.
your eyes
Then I'm not sure.
checked.
It may be the reflection of the blue sky indeed. Yeah. I'm not sure. Let me think about it. Thank you for the question. That's an excellent question.
If you think about
Like an
indoor swimming pool, yeah.
I can't hear you very well.
Oh,
it's
sorry.
too soft.
I don't know what's going on with my mic, but I was
Now I
gonna
can hear you.
say, oh, cool. Okay. I was gonna say, if you think about like an indoor swimming pool, that typically looks pretty blue. So maybe it's more about like the volume of the water that you're looking at than, yeah, like maybe having just like a glass of water isn't enough to scatter a large amount of blue light.
So that's definitely there. So depending on the amount of water, it may look totally clear or it may look bluish. So I'm sure that's part of the factor too. And now I'm trying to remember what I learned in the past. There's also the issue of the absorption of light, actually, in the case of water. And if you go to deep, if you do diving and go very deep, you don't see any red light anymore because red light tends to be absorbed by water molecules. And of course, what wavelength of light get absorbed depending on the atoms and molecules. So it's not universal, but the red light tends to be more absorbed than the blue light. That's why if you go deep in the ocean, everything looks blue down there. You don't see anything red. And so that's so you probably have to factor in all three of these things: reflection of light, absorption of light, and amount of water you have in a given volume that would you are looking at in the case of especially ocean, and all these things I'm sure that will come in. But let me also think a bit more about and try to come up with a more clear explanation of that. Thank you, Dorothea. Any other questions about this? Okay, all right. And of course that you know that the red light has a long wavelength, and then the green light, yellow light, and the blue light. And so so this is the way actually different lights come into your retina. And what's going on here is that you have three basically filters looking in your retina. That one filter selects red light, one filter selects the green light, one filter selects the blue light, and that's why our vision is based on RGB. And if you ask the question, why doesn't the sky look violet instead of blue? Because the violet light has even bigger cross-section than the blue light. My understanding is that that's because our eye is less sensitive to violet compared to blue. So sensitivity curve goes down towards the shorter wavelength before it gets into UV. So even though the sky scatters more violet light than blue light, our eyes are less sensitive to the violet light, and hence the sky looks blue. And the same thing with the sunset. So if the sunset at the sunset, the light all the blue component light gets scattered away, then of course what comes the most to your eyes is the red light. But the sunset is rather orange than red. And that's once again, if you go to very red and long wavelength, the sensitivity or retina goes down. And that's why sort of weighted sum is peaked around orange at the end of the day. So you are now very sensitive to the extreme wavelength of violet or red. So even though the sky is actually violet, you perceive it as blue. And even though the sunset is actually red, you perceive it to orange because of the sensitivity curve. And at least that's the way I understand it. So I'm not a biologist, so I can't vouch for it, but that at least makes sense to me. Any questions about this argument? All right. And this is the spectrum of the light coming from the sun. And compared to this ideal black body radiation coming from a surface temperature of about 6,000 degrees for the sun, it's actually suppressed at various wavelengths because of the absorption of light by the gas on the atmosphere of the sun itself, and also atmosphere of a planet. So it is a big reduction of the light coming from the original black body radiation to the light that reaches the surface of the Earth. And in this area, you see big dip, and that's because of the absorption due to the OH molecules of the rotational levels, which is in an near infrared, which is a big issue when you actually do astronomy. So I'm actually building a new spectrograph for a telescope, and because the atmosphere absorbs so much infrared light, which also emits infrared light. So when you do observation of infrared, the atmosphere is a huge background, and you have to actually subtract all these rotational levels of the emission of the infrared light from the atmosphere. So this is a big nuisance over here. And visible light is much better because you don't have a particular lines that would be emitted by the atmosphere. And much of this absorption is done in a way that doesn't affect much of the observation. And if you go to UV though, then you don't get much UV light because this all gets scattered away. So if you would like to do astronomy in UV, you need to send up satellites. It's very difficult to do on the ground. So just by looking at this kind of spectrum, you already see challenges in doing astronomy. And also the fact that our eyes evolved to be sensitive to the center region of the spectrum kind of makes sense, where information is the clearest using the sunlight we get from the 6,000 degrees of the surface temperature. So now you understand this picture, the sunset is orange. All right. And I see 8 chats. Now we're going to do QFT underwater. Yeah, you should do that. This is why stoplights are red. I thought correctly. Sun gets to yellow, then green. Oxygen in the water. Yeah, so this is about this absorption I just briefly mentioned. So I think you're right, Miguel. Good. All right. So the final subject I'd like to talk about the scattering process is the idea called resonance. I did mention this a little bit before, but now this is time to actually really discuss it. So we talked about the scattering of the photon of an atom. But suppose you send in a photon whose energy precisely corresponds to energy difference between 1s and 2p state. Then this photon can excite electron in 1s state to 2p state. Then energy of the intermediate state is the energy of the 2p state, while energy of the initial state is energy of the 1s state plus the energy of the photon, and they are precisely the same. Then you wonder, the cross-section might become infinitely large because energy denominator is 0. But of course, we know the cross-section you measure cannot be infinite. So the way this resolves this issue is that the 2p state actually has a finite lifetime, as we computed before with Fermi's golden rule. And lifetime is the inverse of the rate, gamma, we computed. So it turns out that energy of this intermediate state 2p now has acquired an imaginary part, which is gamma m over 2. And the way you can sort of intuitively understand it is that when you look at the time evolution of state in Schrödinger equation, it goes like e to the minus iet over h bar, right? And then if you square it, it's always 1. So the state would always remain with the 100% probability. But if you're talking about state that is unstable, then the probability should go down like exponential, e to the minus it over tau, where tau is the lifetime. So if amplitude squared goes like e to the minus it over tau, then amplitude should go like e to the minus it over 2 tau. And this e to the minus t over 2 tau can be regarded as the imaginary part of an energy eigenvalue, because energy, e to the minus iet over h bar, if energy has a slight imaginary part in it, that will give you exponentially decaying behavior. And that should correspond to inverse lifetime over 2, and therefore decay rate over 2. So it turns out that when you do the correct calculation of the photon exciting the atom and emitting a photon again, going from 1s state to 2p state in the middle of it, you have to insert energy of the intermediate state, not just the energy of 2p state as the real part, but also need to put in this imaginary part, which is related to the lifetime of the 2p state. That is actually the correct way of computing the cross-section in this case, and therefore cross-section is not infinite. So whenever you see some infinite result in physics calculation, that is a sign that you have not thought through the problem correctly. You have to think about it, and you need to find out where you have made a mistake at the conceptual level. So in this case, the mistake I made initially to observe this infinite large cross-section was that I didn't consider the fact 2p state is unstable. And for an unstable state, energy is not purely real. It has a slight imaginary part that would correspond to the decay rate over 2. And by correctly putting in the energy of the 2p state, including the imaginary part, then the cross-section no longer diverges. It's finite, even when EI minus EM is precisely 0, and you get a finite cross-section. So that is the behavior called resonance, for the reason I'm going to actually mention on the next 2 slides. But let me tell you, if you have any questions about this argument, why unstable state should have imaginary part to its energy, which correspond to the decay rate over 2. Any questions about this? Okay, so I will keep talking about this for the next couple of slides. So if you have any questions about this, you still can come back and ask this question. So how do we see this imaginary part of the energy from the point of view of perturbation theory? Here, I compute the energy shift due to perturbation theory, which I'm sure you have done in quantum mechanics class. And at the second order in perturbation theory, energy shift due to perturbation is given by this expression, which is very similar to this the contribution of the amplitude we talked about. So you have the matrix element of initial state going to the intermediate state I using this interaction Hamiltonian, and coming back to the initial state using the same interaction Hamiltonian, and you have the energy denominator. But having developed this time-dependent perturbation theory, we need to have this I epsilon to make sure that all the time integrals involved in a time-dependent perturbation theory would converge. So we put in this I epsilon as for our convenience to make sure all these time integrals converge when you send the time interval to infinity. But we decide to keep it because this is a moment we actually need it. So energy shift, a second order perturbation theory, is this matrix element squared over EI minus E intermediate state I, which I believe we have seen in quantum mechanics class. But when you consider the possibility that E little I and E capital I might possibly be the same, you have to retain I epsilon to avoid infinities. And how does this I epsilon help at the end of the day? So that's where you need to rely a little bit on this complex analysis of the contour integrals. And when you look at any textbooks of the contour integrals, this 1 over x plus I epsilon is given by integral according to this contour. So this cross is the origin in complex x plane, namely x vanishes here. And if you have 1 over x, then integral goes right through this 0 in the denominator, then you have infinity. And you don't know what to do with it. So idea of this I epsilon is to move the location of the pole to negative I epsilon. So this cross is moved slightly downwards to negative I epsilon. So your contour is now defined to go above the pole, not through the pole. So that idea of defining a contour above the pole is depicted by this cartoon. So if you have a pole, putting I epsilon in the denominator forces you to follow this path to avoid the pole above it, not through it, not below it, but above it. That's what this I epsilon is telling you. And then I can divide up this contour into 2 pieces. One piece is the straight axis coming close to the pole and starting away from the pole. And some of these 2 segments is what is called the principal value integral. Namely, this is an integral over 1 over x, but you avoid this area of the pole equal distance before and after the pole, and integrate over the rest of the real axis. And that's the definition of this principal value integral 1 over x. And this second term is this semicircle. And if you remember, the integral of a pole with a full circle gives you minus 2 pi I in the clockwise direction. But normally you think about this anti-clockwise direction, that's 2 pi I. So full circle around the pole is minus 2 pi I. But here, this is a semicircle. So it's half of the full circle. That's why I get minus I pi. And the residue meaning you substitute x equals 0 to the rest of the integrand. And that's nothing but a delta function. So this is the general formula for the contour integral when you have a pole, and if you are avoiding the pole for your particular contour, then integral using this I epsilon prescription is the sum of the principal value integral and the piece coming from a delta function. And because the full circle integral is always pure imaginary, 2 pi I, the semicircle integral is also pure imaginary. And that's how you find the second order energy shift gives you a complex result. Energy is shifted into a complex plane. Energy is no longer pure real. And then you can easily see then what the imaginary part of the energy shift is. So imaginary part of this delta E, the imaginary part from this I epsilon prescription. So I rewrite this denominator, 1 over EI minus E capital I plus I epsilon in terms of principal value integral and I pi times delta function. And I just look at the I pi piece because I'm interested in the imaginary part now. And that is given by this minus I pi. And energy denominator is now replaced by this delta function with a matrix element squared. But now if you look at this expression looks very familiar from Fermi's golden rule. This sum of matrix element squared times 2 pi times delta function over h bar is the rate. So this whole thing turns out to be the rate over h bar over 2. And I realized that I actually mixed up 2 notations here. I apologize. So on this slide, I used W as the rate and gamma as the h bar times the rate, which has the dimension of energy. So gamma here has the dimension of energy now. And this gamma is therefore h bar over the lifetime or the rate. So in the case of 2p state, now you can see that imaginary part of the energy of the 2p state is really the same calculations you have done for the lifetime of 2p state times h bar. So the rate times h bar has the dimension of energy. So it qualifies to be part of the expression of the energy shift, but it's an imaginary part of the energy shift. So that's how you find that energy of the 2p state is now shifted with an imaginary part in it. And then if you plug in this new energy together with this imaginary part into the usual time evolution of e to the minus IET over h bar, now that energy has this imaginary part, absolute square of the time evolution will give you this exponential decaying behavior. And that's how you know that this imaginary part of energy you computed here really does correspond to the lifetime of the state. And that's how everything hinges together. So let me repeat this once again. We had this apparent paradox that some cross-section seems to be infinite. But this problem can be avoided if you accept the fact that energy of the intermediate state has a slight imaginary part in it. And this slight imaginary part is nothing but the consequence of the energy shift at the second order perturbation theory. And thanks to this I epsilon we derived from the time-dependent perturbation theory to make sure that all time integrals converge, this I epsilon would dictate this particular contour to go around the pole. And this contour has this semicircle in it. And semicircle would give you imaginary part of the energy shift, which is precisely the same thing as computation of the rate we did with the Fermi's golden rule. And therefore, you obtain the imaginary part of the energy shift, which is given by minus I h bar times the decay rate over 2, which has the correct dimension of energy. And if you put in this h bar decay rate over 2 into this exponential factor of the ordinary time evolution in Schrödinger equation, it correctly gives you exponential decay behavior of that state. And hence you can identify the lifetime, which is given precisely by h bar over gamma. And this gamma ends up also having the meaning of something called the width of the resonance. And that will come up on the next slide. But I hope this argument is clear. All I did is to apply the formula you have known from quantum mechanics class on computing the second order energy shift. I believe you have done this kind of example using the Stark effect in the neutral atoms, right? Once you apply electric field, energy shift at the second order in electric field, and that's a Stark effect, and that is how you compute that energy shift. The only thing new here, which we derive from the time-dependent perturbation theory a little bit more carefully, like than what you might have done in quantum mechanics class, is this I epsilon piece in it. And this I epsilon piece would tell you that energy shifts does have imaginary part, which precisely corresponds to the Fermi's golden rule of the decay rate. And therefore, imaginary part has to do with the decay rate with a factor of 2. And when you take the absolute square of the usual energy dependence, time dependence of the state, this imaginary part would give you exponentially decaying profile, and therefore it does have to do with the lifetime of the state. So when we actually discussed how to compute the lifetime of 2p state, we used the Fermi's golden rule and computed the rate. But I did not fully justify why that was the same thing as the lifetime of the exponential decay law. Now I justified it. I had the argument before, now once you have the decay rate on dimensional grounds, that must be the same thing as inverse of the lifetime. But I didn't quite justify the exponential behavior. Now I do. By just plugging in this imaginary part of the energy shift, you clearly see that this is an exponentially decaying behavior as a function of time. And then you can really identify the lifetime of this exponential profile. Then you can easily see that lifetime is indeed inverse of this imaginary part of the energy times factor of 2. So that's the argument here. And then I hope everything comes together why we needed to keep this imaginary part of the energy of the 2p state in this calculation of the cross section so that it doesn't diverge. And the origin of this imaginary part really has to do with the lifetime of the state coming from the second order energy shift. Okay, let me pause here. Are there any questions about this? Is it okay? Okay, I got only 3 minutes left, so let me show this correspondence to the idea of the width. So now that we have this imaginary part in the energy denominator, if you think about energy of the photon you send in to be very close to the energy of the excited state, then everything else can be considered to be more or less constant. Then you have a peak when EI becomes the same as EM, because gamma m is a small number. Then you have this behavior of what is called the Lorentzian curve. Well, it's also called Bright-Wigner from the context of quantum mechanics. And then this gamma has a meaning of full width half maximum of this cross section as a function of energy. In the case of atomic scattering process, this width is so narrow that you see just a single spike that looks like a delta function. But when you go to processes in nuclear physics or particle physics, then you see sometimes the lifetime of the states to be very short, and hence inverse lifetime, namely this gamma, to be fairly large. Then you can observe this Lorentzian curve of this width, full width half maximum of the cross section as a function of energies. And here is some of the data, let's see, this is actually the same thing I mentioned earlier, so I'm going to come back and talk about this later. And that's the same phenomenon as a resonance in harmonic oscillator, but I just want to show you some data. So this is a scattering cross section of very slow neutron on uranium nucleus. And the neutron can hit the excitation energy of uranium-239. So then the neutron is absorbed by the uranium nucleus to become some of the excited states of uranium-239. And then decay back into 239 ground state by emitting a photon. So this cross-section can show again a peak when the energy of the neutron is precisely that corresponds to the energy of the excited uranium-239. So you see these bunch of peaks But each peak is not delta function. You do see finite width. And that's the idea that lifetime of this excited state is fairly short. Inverse lifetime is fairly large. That corresponds to the width of this each resonance. Namely, you are already observing that energy has a finite imaginary part in it. And that show up as in data as the width of each of these peaks. And if you further go to particle physics, you see these peaks where you clearly see a finite width, because lifetime of this state is so short. And lifetime in this case is coming from the scattering of photon sent into a proton. And you may have never heard of this, but proton has an excited state. Proton can be excited. And this photon corresponds to the excitation energy of the proton. So it gets excited to a state called delta, capital delta. But that delta state is so short-lived at the level of 10 to the minus 23rd second, is so short-lived. Inverse of lifetime is a big number. And so what you're seeing is the width of that state in the scattering cross-section. So in atomic transition, as I said, width is so narrow, energy is so well defined, you see basically delta function peaks. But if you go to nuclear physics and particle physics, there are states which have fairly short lifetime. So you do observe this width in this Lorentzian curve of the cross-section. So that's what I want to tell you as the final message today. And then I just go through some of these math aspects of this energy time uncertainty to conclude this discussion and finish up the discussion on resonance on Friday. And once I do, we can finally move into Lorentz invariant quantum field theory of spin zero particle, spin 1/2 particle, and so on. Develop the Dirac theory, Klein-Gordon theory, put everything together into quantum electrodynamics, work out the Feynman diagrams, and that will be the rest of the class for this semester. So you're now coming to the end of this semester, getting into the Lorentz invariant QFT. And before going to do that discussion, I'm going to finish up this discussion on resonances. Okay, any questions? All right, then I see you on Friday.
Thank you.
Thank you.
And I'm getting the second shot of vaccine this afternoon, so I'm excited.
Yay.
Watch out! I got my second shot yesterday, and I definitely am pretty tired. So
Okay.
Yeah.
So I'm gonna be tired after this then.
Maybe, but maybe not, because yeah.
Okay. I'll find out.
Bye.
Bye.